Welcome to This Explainer. Today, we're going to peel back the layers of everyday words and discover the fascinating, incredibly computer-like code that powers human speech. Have you ever stopped to think about what's actually happening when we talk to each other? I mean, on the surface, it seems so effortless, but underneath, there is a highly structured, remarkably precise system at work. Here's our roadmap for today. We'll kick things off with making sense of sound, test things out with the minimal pair test, meet the phoneme, dive into the DNA of sound, see rules and natural classes in action, and finally wrap up with the binarism debate. Let's get right into it.
All right, part 1, making sense of sound and the real problem of speech.
We really have to start with the problem of speech itself. Think about it. Acoustically speaking, the sounds coming out of our mouths are literally just this blurry, continuous stream of sound waves. There's a vast, messy continuum of sounds we can physically produce. So the crucial puzzle we need to solve is this. How exactly do our brains take this continuous noise and instantly chop it up into distinct, meaningful building blocks? Because our brains definitely don't care about every single acoustic detail. They're only listening for a very limited set of distinctions. The question for linguists then becomes, how do we prove which distinctions actually matter to the human mind?
Which brings us to part 2, the minimal pair test and swapping sounds.
To figure out which phonetic contrasts our brain actually cares about, we use something called the minimal pair test. Take a look at hat and cat. Notice how making one simple mental swap, trading that H sound for a K sound, completely changes our reality and the entire meaning of the word. We have hat on one side, cat on the other. Just one tiny sound changes at the very beginning, but that single change shifts the whole meaning. It's absolute proof that the contrast between an H sound and a K sound is highly relevant in English.
So, formally speaking, a minimal pair is just two sound streams of the exact same length where exchanging just one sound for another results in a total change of meaning. This proves that the presence of a specific sound over another in a specific spot is incredibly important to our brains. We don't just care that some sound is there, we care that it's this sound and not that sound, because that choice is the key to unlocking the word's meaning. Moving right along to Section 3, Meet the Phoneme, our abstract category.
Okay, now that we know what our brain is actively listening for, let's zoom in one level. A really brilliant way to think about this is that a phoneme isn't just one rigid, perfectly identical sound every single time you open your mouth. It's actually a category or a set. Take the word data. Whether you pronounce that middle consonant as a crisp T sound or maybe a softer tapped sound like we tend to do in American English, the meaning of the word doesn't change one bit. Your brain just lumps those different physical sounds, which linguists call allophones, into the exact same abstract bucket. And that bucket, that is the phoneme. Now, if you map this out, it's pretty wild. Our mouths systematically organize these phonemes on a literal grid, based entirely on where and how the sound is produced. We look at the manner of articulation, like, is it a sudden stop of air, a continuous breathy fricative, or a nasal sound? And then we look at the place. Are your lips pressed together for a bilabial sound, like p or b? Is your tongue tapping the alveolar ridge right behind your teeth for a t or d? It's like every single phoneme in a language has its own specific GPS address in our biological system. Let's dig even deeper in Section 4, the DNA of sound and attribute value structures.
Here's where things get incredibly precise. Linguists break these phonemes down into what are called attribute value structures. Honestly, think of these like a motor program or a sheet of music telling different parts of your vocal tract exactly what to do. You've got the attribute of place, telling you where to make the sound. You've got manner, telling you how to make it. And you've voice, which literally just dictates whether your vocal cords should be vibrating or not using a simple plus or minus value. It is quite literally a biological instruction manual for speech.
Just look at the difference between a b and a p. It is a simple toggle switch of that voicing feature. Everything else, the bilabial place, the stop manner, is perfectly identical. The only difference is that for b, the voice attribute is set to plus, meaning the vocal cords vibrate. For p, that voice attribute is set to minus. I mean, it looks exactly like a line of computer code being rewritten, right? It proves that way beneath the actual sounds we hear, our brains are processing these distinct independent features.
So, how does this actually play out? Let's look at Section 5, Rules and Natural Classes. Phonology action.
You might be wondering, okay, why do these microscopic toggle switches matter outside of a textbook? Well, let's look at a real-world plot twist from the German language. German has this specific phonological rule for words that end in a voiced consonant, like the word grob, spelled with a B at the end. The rule basically says that when a voiced consonant hits the absolute end of a word, you just toggle that voicing feature to minus. That's it. So the B, which has positive voice, flips to a negative voice and actually comes out sounding like a P. It proves that our mental language rules are operating on these invisible features, like simply switching off the voice, rather than us relying on a giant random lookup table of entirely different sounds.
And this is exactly why the concept of a natural class is so vital. A natural class is just a set of sounds that share a specific feature, like all sounds that are positive for voice or all sounds that are stops. Because they share these specific feature toggles, they form a natural class, which allows linguistic rules to apply to whole groups of sounds uniformly. That German devoicing rule? It doesn't just target a b, it targets any consonant at the end of a word that has a positive voice feature, stripping that voicing away perfectly and uniformly across the board. It's amazingly efficient. Which brings us to our final section, part 6, the binarism debate and the structuralist conflict. Zooming into the deepest layer of this code, we hit binarism. This is a hot debate over whether all these phonetic features truly boil down to just positive and negative values, exactly like binary computer code. Thinkers like Roman Jakobson were huge advocates for this, suggesting absolutely everything in language could be defined by a simple plus or minus. But is language really just ones and zeros? Sometimes, trying to force human sounds into strict binary cuts leads to some pretty artificial results. For example, when you have 3 places of articulation, like bilabial, alveolar, and velar, trying to divide those 3 things up using just a 2-way binary switch gets really clunky. Because of this friction, structuralist linguists clash over how to actually define these oppositions. Are they equipolant, meaning completely symmetrical, where both sounds just have different but totally equal features? Or are they privative? In a privative opposition, one sound has a feature, making it the marked version, while the other sound simply lacks it, acting as an empty, unmarked baseline. If voicing is privative, a bud is quite literally just a pud that's been stamped with a special voice mark. It completely shifts how we view the very architecture of the sounds we make every single day. As we wrap up this explainer, I want to leave you with this massive question, right at the heart of this structuralist debate. When you speak your very next sentence, are you just running a highly complex biological algorithm of ones and zeros? Are you seamlessly toggling tiny invisible switches of airflow and vocal cord vibration at lightning speed entirely subconsciously? Think about it. The next time you say a simple word like cat or hat, take a second to appreciate the staggering, systematic code firing off in your mind just to make it happen.